So we're going to start talking about improper integrals in this video. And before we start to define that, I just want to go back and look at the fundamental theorem of calculus. So we've made a lot of use from that theorem, and it's a very powerful theorem. But if you'll recall, the hypothesis or the assumption we were making when we could use it is that the integrand was continuous on the entire closed interval from a to b. And then, of course, that we could find a big F of x that was the antiderivative of the integrand. So there are cases where we can't directly apply FTC, and these are what we call improper integrals. Now, there are different ways that you can have improper integrals, and really there's two things that I want to point out in this theorem. So, of course, one of the things that's important is that the integrand be continuous over the entire interval. If you have discontinuities in the interval, then that means you have an improper integral. That's actually what we're going to talk about in a different video. More immediate that we can focus on here is that we have this closed interval from a to b. And because it's closed there, we don't really consider a or b being infinite, plus or minus. And in the instances where that does occur, again, that requires us to rethink FTC. So we're going to look at improper integrals that arise from looking at the limits of integration and what we do when either a is minus infinity or b is positive infinity, or both of those things are true at the same time. So that's the focus of this particular video. So to start with here, let's consider the case where b is positive infinity. So if I encounter an integral that's from some fixed constant a to positive infinity for a function f of x, well, we are assuming here that we don't have discontinuities. I'm going to focus on that in a separate video. But here, what I want to think about is that the problem right now, potentially, is, of course, this up here, because we don't have FTC for a situation where we don't have a finite interval there. Well, we know how to handle if we integrate from a up to some fixed b. So let's put a placeholder in there, b. And if I want to consider not just a fixed b, but infinity up there, well, after I use FTC on the integral, let's send b to infinity. So we turn this into a limit problem. We're going to bring in this this language of convergence and divergence, which again, we're going to see in different instances throughout the course. So we're going to say that I'll use green here for converges. The integral converges if the limit we're taking up here exists and is finite. Otherwise, it diverges. So notice with that, there are different ways. You can find that limit and it doesn't exist. That means it diverges. You can find that limit and it exists, but maybe it's plus or minus infinity. That also means that the integral diverges. So let's see this in practice. Here's an example where a is 1 and we see b is infinity, and we want to evaluate this integral or show that it diverges. So first of all, I'm going to note, just to make this easier on myself, that's x to the minus 4. So according to our definition above, what I want to do is take this and express it as a limit. This is the way we define this. And I'll point out that it is important that you use this notation. A lot of times people put infinity on the evaluation bars, but what does it really mean to plug infinity into a function? So we really are thinking about this as working our way from the inside out. Let's find this as a function of b, and then in the last stage we can send b to infinity. Well, the antiderivative of x to the minus 4, make sure I write my limit here, is negative 1/3 x to the minus 3. We're evaluating that from x equals 1 to x equals b. So I've got here negative 1/3. When I plug in my bounds, I'm going to have b to the minus 3 minus 1 to the minus 3, which is just 1. And of course, now I'm going to take the limit. And what I'm going to focus on is what happens to this term as b goes to infinity. Well, remember that that's the same thing as 1 over b cubed. So as I send b to infinity, that's going to vanish. So we're left with negative 1/3 times negative 1. So we get 1/3. So in terms of what we say here, it depends on, I didn't really put any text here, but you can say here that this integral converges, because we got a finite limit. You can say that it converges to 1/3. Sometimes a problem might simply ask you to decide whether an integral converges or diverges. You don't need to specify that it converges to 1/3 in that instance. Sometimes you'll see a question asks you to evaluate the integral or show that it diverges. So evaluate means that you would want to include there that it converges to 1/3. But either way, this is an example where you can see that we get convergence here. So we're going to see a very similar approach to having a, I went too far. There, that's what I wanted to do. To have a negative infinity in place of a with a fixed finite value b up top. So we're going to approach this as a limit where we send a to minus infinity and then apply FTC to our integral from a to b. So the only thing that's different here is what we're sending to an infinite value. Just like we saw above, convergence and divergence have the exact same meaning. If that limit exists and is finite, the integral converges. Otherwise, we're going to say it diverges. So we're going to handle this much in the same way. So in this case, we see that I could take the original integral and I want to rewrite this as the limit as a approaches minus infinity, the integral from a to 5 e to the minus x. Now the antiderivative here is negative e to the minus x, and we're evaluating that from x equals a to x equals 5. And we're going to get here negative e to the minus 5 minus a negative plus then e to the minus a. Okay, so again, in terms of trying to decide whether this converges or not, we focus on the limiting part here. So we have to be a little bit careful. A is going to minus infinity, so minus a is going to positive infinity. So what's going to happen here is that we're going to have this negative e to the negative 5 plus something that's growing without bound. So the limit exists, but it's positive infinity. So even though the limit exists, it's not finite. This integral diverges. Now with divergence, you don't say to infinity or anything like that. We just simply say that it diverges. And I'm realizing now I would say in our previous example, I should have added the text, this integral converges to 1/3, and I already addressed that the directions will specify kind of what you'd have to say. So here we see what would happen when you have divergence, but we're also seeing how to handle the lower limit of integration being infinite. And then the last thing to consider with regard to infinite limits of integration is what if both of them are infinite? So what we can build off of here is we know how to deal with a positive upper limit by itself and we know how to deal with an infinite upper limit by itself, and we know how to deal with an infinite lower limit by itself. So to take advantage of that, the way we're going to define this is as, I'm going to define it as the limit as a approaches minus infinity, the integral from a up to any c that I'd like, doesn't matter, we'll see, plus the limit as b approaches positive infinity, where we integrate from that same c value, importantly, up to b. Now, a couple things. Notice what I'm doing. In some sense, I'm taking advantage of the fact that we can rewrite the original integral using our integration properties, break that into 2. And then what I've got on the right-hand side here is how we defined each of those respective integrals. So we still have the notion of convergence and divergence, but we have to be a little bit careful here because there's two limits to contend with on the right-hand side here. So in this instance, convergence means that both of the integrals on the right converge. More specifically, that means that individually, both of these limits have to exist and be finite. We don't want to try to combine them. We're really looking at each of them separately. If either one of them does not exist or is not finite, the integral diverges. So I'll really emphasize here that both is really important. So we'll finish this video off with one example where we can see this in practice. One of the things I'll emphasize in here is the C value is intentionally vague. Often I just choose 0. It really doesn't matter. So with this here, I'm going to take what we're starting with and I'm going to break it up. Like I said, you can pick any number you like to break up the interval. I'm going to split it at 0. So we're writing this as the integral from minus infinity to 0 plus the integral from 0 to infinity. And then I'm going to express each of those individually as a limit. One thing I'll point out, so in this point, I can write this as the limit is a goes to minus infinity, the integral from a to 0. And this is the limit as b goes to positive infinity, the integral from 0 to b. It is completely fine if what I wrote in the second line here is what you jump to right away. I'm just kind of adding in the extra detail there. So one thing we want to consider is the antiderivative in this case is arctangent. So maybe to give myself enough room, I'll put this here. So in this first integral, we're evaluating arctangent from a up to 0. So we're going to take arctangent of 0 minus arctangent of a. And then in the second one, we have the exact same antiderivative, arctangent, but we're going to take arctangent of b minus arctangent of 0. Okay, so now we need to think about arctangent. Arctangent of 0 is 0. So one thing that is helpful in this instance, because remember arctangent is an inverse function. Maybe I'll put this in a different color. And I'll put this down here, so I'm going to leave some space. If y is the arctangent of x, that means that x is the tangent of y. So we're kind of interchanging the roles of the variables. So when I said that the arctangent of 0 is 0, because we're trying to say what value of y is equal to the arctangent of 0, well, 0 would need to be the tangent of y, and I know that that means y is 0. So that's the way I'm interpreting this. Now, it might seem a little bit strange with infinite values, because again, that's a limiting idea. So in this first part here, I want to know what the arctangent of a is as we let a go towards minus infinity. So to be clear here, we're saying that in finding this arctan, we're think of a here as playing the role of x. So we're letting this go towards minus infinity, and we want to know what happens to y. Well, that means that in this idea, we're thinking that x goes to minus infinity, and we're thinking tangent of what value would represent that. Well, there are a couple ways to think of that. I sometimes think it's helpful if you've got a good idea of the tangent graph. Remember that tangent has these asymptotes, and they occur at minus pi over 2 and pi over 2, and then of course infinitely other many places. But when we're looking at inverse tangent, we're restricting ourselves to this view. So if you're interested in thinking about in this tangent perspective, when the output of tangent approaches minus infinity, what is the input approaching? Well, look at our graph. When the output is approaching minus infinity, the input seems to be approaching minus pi over 2. So when I come back up here, this first part, I can replace my limit with that. Similarly, with the second one, when the output of the tangent graph is approaching positive infinity, the input is approaching positive pi over 2. Oops, I should write that. Positive pi over 2 minus 0. So the other thing, just to be clear with this graph, if this is how I'm looking at this, this is like my y-axis, so it seems a little strange probably that we're using this, but this is only because of the inverse property here. And then the other thing I'll point out is it might be helpful for you to think of tangent of y as sine of y over cosine. So when the denominator is 0, that's when we get these plus or minus infinities. That's at cosine is 0 at pi over 2 and minus pi over 2. And the distinction between the positive and negative is that sine of pi over 2 is positive and sine of negative pi over 2 is negative. So just a little aside about looking at those limits. Now, to go back to our notion of convergence, this plus I have here is kind of the dividing line where we broke this up into two integrals. So before I do anything, I need to make sure that on either side of this dividing line, I got a limit that exists and is finite. We did over here and we did over here. That means that the integral converges. And just like we talked about convergence before, we've shown that it converges, and in fact, we've shown that it converges to pi over 2 plus pi over 2, so it converges to pi. And like I said, we'll see examples of this, but if either of these things here either didn't exist or was infinite in some way, we pause, we don't even have to look at the other, and we would say that that diverges.